And SRAM has the attributes of being very fast, but it's not very dense because it requires a number of transistors per memory cell. And it's relative, and because of that, it's also relatively expensive. Okay, so SRAM, it's fast, but we pay for it in terms of density and in terms of cost. And so we typically use SRAM in areas where we need fast memory, but we don't necessarily need a lot of it. And cache, which we're going to talk about later, is one prime example of where we use SRAM. There are others, of course. The other basic type of RAM is DRAM, dynamic RAM. And we call it dynamic because it does not keep its value indefinitely, even if power is maintained. A DRAM cell basically consists of a capacitor and a transistor, and that capacitor, because it's so small, discharges relatively quickly, and therefore a DRAM cell has to be periodically refreshed. And so that, of course, requires circuitry to do that. However, DRAM is relatively dense. A DRAM cell is quite small. It's a transistor and one capacitor, so you can get a lot of them onto a silicon wafer, and therefore it's relatively dense. And it's also cheap. However, it's power hungry, and it is relatively slow. Okay, so we use it where we need lots of memory cheap, but not necessarily fast. So, you know, your main RAM in your computer is probably DRAM. So those were the two different types we looked at. And now we're going to finish off by looking at how SRAM and DRAM can be organized, and some of the functionality that's been added to these memory chips in order to improve performance. So we're going to talk briefly about asynchronous DRAM and synchronous DRAM. And basically the difference is an asynchronous DRAM chip, there's no clock signal. And therefore things happen whenever some control signal tells them to happen. A synchronous DRAM chip will have a clock signal applied to it, which gives us some functionality that we'll talk about later. But let's focus on asynchronous first. So in this example, we have a 256 megabit DRAM. So that means there's 256 megabits or cells. And of course, we typically organize those into words somehow. So this could be configured, for instance, having 32 mega 8-bit words, okay, or bytes. So that can be arranged in a number of ways as well. And so in this case, it's arranged in a cell array that consists of 16K words, rows. Okay, so there's 16K rows, and in each row there's 2K bytes, or 2,000 bytes, where a byte, of course, is 8 bits. And when we access something out of this particular memory chip, we're accessing 1 byte at a time. So there's 8 data lines external to this chip. So 8 of the pins on this chip will be the 8 bits of a word or of a byte. So when we apply an address to the address pins, we're going to be choosing one particular byte in a particular row in this cell array. Okay, and that particular byte, its 8 bits will be sensed by the sense-write circuitry, and then those 8 bits will be applied to the external data lines, the 8 external pins on the chip. Okay. So in order to access one particular byte amongst 2,000 times 16,000 bytes, we're going to need 25 address lines. So your address has to be 25 bits long. Okay, so some of those, the upper 24 minus, so that would be how many? That would be 13 bits. 24 minus 10 is 14, 14 bits. The upper 14 bits of the address is going to choose one of the 16K rows, okay? Because 2 to the 14 is 16,000, or 16K, okay? So these upper 14 bits will be latched into the row address latched. At a particular time indicated by the RAS, or the row address strobe. Okay, so when this control signal, and that control signal is not tied to a clock, hence it's asynchronous, but whenever the control circuitry decides that there's an address here that we're going to get the byte for out of this cell array, this signal is going to go low, and then these 14 bits are going to be latched into here. They will then be decoded in order to choose the appropriate row in this array. Okay? The lower 11 bits of the address are going to specify which of the 2,000 bytes in that particular row is going to be accessed, either for a read or a write. Okay? Because 2 to the 11 is 2K. Okay, so these bits will choose the row, and the lower 11 bits will choose the column, if you want to call it a column, where each column is 1 byte, and there's 2,000 columns in a row. Yeah.
If you weren't given the like the 10 minus 0, could you know how big the column is just by looking at like the 32 megabytes by 8-bit words? Like, or would you have to be given?
You'd have to know this.
Yeah. Okay. So that has to be.
Because this could be configured in a number of different ways, right?
Yeah. Okay.
I mean, I could have 32 million rows of 1 byte each, right?
Yeah. Yeah. Okay.
Yeah. Okay, and so we also have a column address strobe signal. Again, this would be a control signal that, you know, when this address is valid here, this control signal would go low, and then these lower 11 bits would be latched into here, decoded, which would choose the sense write, which would choose the 8-bit lines for the particular byte in that row in order to either read the data out or write the data in to that particular byte. Okay, so that's how this particular chip is set up. So use of control lines with no clock obviously makes this asynchronous. Column decoders are used such that we have a 16K by 16K array. We have 16K rows, and you have 16K bits in a row, although we organize them into 2,000 bytes. So that requires 25 address pins, right, as we talked about here. Now, obviously, address or external pins on a chip are expensive. We want to have as few pins as possible, and therefore, what we can do is we can multiplex these address pins, meaning that we only really need 14 pins total. At one point in time, those 14 pins could have the address for the row on them. This goes low, that gets latched into here in order to choose the appropriate row. And then the address on the 14 pins here is changed such that it contains the address for the particular column we're interested in. And then this signal goes low, latches that into here, and chooses the column. Okay, so the row and address, and column address don't get latched in at the same time. The row, for instance, would get latched in first by this signal going low, and then that address is replaced on those 14 bits with the 11 bits for the column, and then this goes low and that's latched in here. Okay, so we can get away with fewer address pins just by using the same pins for the row address and the column address. Obviously, just not at the same time. Okay, so we multiplex them. And obviously, that's why we need the RAS and CAS, the row address strobe and the column address strobe control lines. And then the only other thing we need, of course, is since this is a DRAM chip, all of the values in here have to be periodically refreshed, and we're talking, you know, tens of milliseconds. Every tens of milliseconds, these have to be refreshed. And so it's not shown here, but there would be circuitry that would do that, and typically that's done by reading those cells, which doesn't mean you necessarily have to put those values on the data lines, but just the operation of reading a particular cell, the sense write circuitry will refresh that cell, right? If the capacitor is discharged a little bit, it'll charge it back up. If the capacitor is charged a little bit, it was originally at 0, but for some reason it charged a little bit, then it'll drop it back down to 0. That's what happens with the refresh. Okay, so that's what we mean by asynchronous DRAM. No clock signal. These control lines are what especially control when the address is read. Okay, well that implies that we need a little bit of circuitry somewhere called a memory controller, which is going to be an intermediary between the processor and this asynchronous DRAM chip, okay? Because the processor needs to work with any type of memory, and so it only provides the basic information. It provides the address, whether it's a read or a write, and then some other circuitry perhaps, or signals like a request line and a clock signal if the chip needs a clock, okay? Then we have the memory controller, which is going to, for instance, if we're talking about an asynchronous DRAM chip that's over here, where we multiplex the address pins, well then the memory controller has to do that. It has to either put the row address on those address lines or the column address and then activate the appropriate strobe signal, okay? And of course, it's got to tell the memory whether we're reading or writing, and because we have multiple memory chips on a memory board, we have to choose the appropriate chip with the chip select control signal. And the clock, if this is a synchronous, which we're going to talk about next, it also has to provide a clock, obviously. But the data doesn't have to go through the memory controller, it just goes right between the processor and the memory. Okay, else there that, oh yeah, and it's also responsible for the refresh cycles. So the memory controller can be doing the refreshing here as well. So let's, okay, but before we get to synchronous, fast page mode is, of course, we're always trying to get stuff out of memory as quickly as possible. And often, we don't read just one word out of memory. In our simple assembly language programs, that's what we do. But you know, when we're transferring a file, say from a hard drive to the desktop on your computer, you're not just transferring one word of information, you're transferring a whole block of information, right? So that's typically what happens, and therefore we're trying to optimize in how fast that happens. So fast page mode is one way we can do that, because this is the same setup we just looked at. When you choose a particular row address and latch it in and decode it, you activate the whole row, okay? All 2,000 bytes in that row will be activated. So if you need, let's say, half of those bytes, because you're transferring a block of information, not just one byte, but say you need half of those, 1,000 of those bytes, rather than apply the row address, latch it in, apply the column address for the first byte, latch it in, go get it, okay? Now we need the second byte in that row, okay? Well, then you can put the row address here again, latch it in, activate that same row again, put in the address for the next column, read out the 8 bits in the next column of that row. Rather than doing that, since we need a bunch of bytes from that row, just activate the row once, okay? And then you can just keep that row activated and just activate one column after another and read them out. Okay, that's what we call fast page mode. So you just have one RAS cycle. So this just goes low once and it latches in a particular row. And then we can just keep changing the column address here and activating this to go from one column to the next. That's all it is. Okay, so these are all tricks that computer engineers over the years have come up with in order to make memory access more quick. Because as I keep saying, the big bottleneck in any computer is accessing memory, right? The processors get faster and faster and faster. Memory doesn't improve in speed at the same rate. So that's what we mean by fast page mode, okay? To the big one here. Oh, no. And all right, so let's talk about synchronous DRAMs now. So obviously with a synchronous DRAM chip, there's going to be a clock signal applied to the chip. Okay, so all of this is on the chip. So we've got some additional circuitry here on the chip, which is going to take care or give us some more functionality that we don't have in an asynchronous DRAM chip. For instance, automatic built refresh cycles are driven by the clock. So as with when we have a DRAM chip, an asynchronous DRAM chip, we need that memory controller external to do the refreshing. With a synchronous DRAM, because there is a clock signal on board that chip, we can use that clock signal to do the refreshing or to give us the timing for the refreshing. So that can all be done on board. So you'll see that there'll be a refresh counter up here, which is on board the same chip, which is being driven by this clock, which will just be cycling through these rows and refreshing one row at a time, okay, as driven by this clock. So that it gives us that functionality. The address and data connections can be buffered with registers. So now we have down here, we've got some additional registers between the cell array and the write sense circuitry and the external data pins. Okay, so that allows us to do some stuff like read out, for instance, we can read out a byte from here, we can latch it into here, and while that's still being read by the processor, we can already be accessing, for instance, the next byte. Okay, and the clock signal will just allow us to keep latching it in here every clock cycle. So we can, again, we can access memory a little bit faster, okay? Because while the processor is reading what's in here, the chip here can already be looking at the next address and getting that next value here, i.e. the read-write circuitry here can already be accessing the next byte, and then it can latch it into here, and then it can be getting this while the processor is reading that one out, okay? And we've got latches here as well on the addresses doing the same thing. A mode register is used to set the read-write mode of the SDRAM. Burst operations of different lengths can be specified. So this, again, now we're, instead of fast page mode where you have to keep applying the next column address to get the next byte, we can have what's called a burst mode in a synchronous DRAM cell, again, because we have a clock signal, okay? So instead of having to apply this strobe signal every time we want the next byte in a row, we can just use the clock cycle to do that instead. And the clock can be very fast.
Because there's only these lines coming in.
Yeah. That's a good question. There has to be additional information provided, but they don't show us anything that would give us that.
I mean, if it depended on one of the strobes, as long as it would keep outputting bytes until that strobe changed and then start a cycle again.
Yeah, but I don't think it is how many, what any information shown in this diagram that would give that. Yeah.
So on the diagram,
This, let's go back. Yeah, see, this block diagram doesn't show a lot of detail, but see, these two control signals are coming in here, which, and then there's going to be obviously connections from this block to all of this, controlling all of this, right? So as long as the CAS is high, whatever is coming in here is not going to be latched into here.
I see. So it only gets latched when it's low.
Yep, it's active low. So these address pins are connected to both of these paths, right? These address pins will hold either the row or the column address at any particular time, okay? So both of these are going to be waiting until their appropriate signal goes low, at which time they're going to route that information through. If it's not low, it doesn't go through.
Not active low, sorry, on the other one.
Got to be controlled by the circuitry here, and they're not showing us how that information comes in here. But there's going to have to be some information, maybe by another memory controller that's telling this chip, you know, how many bytes in that row do we want? And then, and maybe I'll draw it here. So we've got a number of columns in a word, or a number of bytes in a row. Here's the second row. Here's the third row, right? And in this burst mode, we're reading all these out one clock cycle. In a double rate, we're reading them out 2 per clock cycle, but you can only access one of these per clock cycle. So what they do is they take, maybe I should use 2 different colors. Instead of organizing it in one bank like that, we can organize it in two banks. So I got the same number. And then here we have our second bank somewhere else. Do I got the same number? This would be 3 by 1, 2, 3, 4, 5, 6, 3 by 6, 18, 9 and 9, yeah. So instead of organizing it like this, we organize into two separate banks. So this memory word is this one, this memory word is this one, this memory word is this one. This one is this one, this one is this one, and this one is this one. Okay? So they're interleaved, and so if functionally what we want to do is this, well, then we got circuitry reading this one out of this bank, say on the rising edge, circuitry controlling or reading out this one out of this bank on the falling edge. Okay, and that way we can do it 2 per clock cycle. So it would be read out like this, in this order, but falling, or let's say rising edge of the clock. These are read out on the rising edge of the clock. These are read out on the falling edge of the clock. Okay? Okay, so that's all that is being talked about.
Put on the bottom right, the bottom there, are you using that sort of circuitry where you have like, you're reading on two different like their outputs? Or?
No, there would still only be one output.
Okay. But you'd have to have that structure where you have two.
Where we have two different banks here.
Yeah, okay.
Yeah, so you can view this cell array now has been divided into two.
Okay.
So there's going to be duplication of some control circuitry, definitely, right? But the number of output pins would still be the same.
Okay, still the same output pins?
Yeah.
It's just it's doing two operations per clock speed.
Yeah.
Double.
Wouldn't the actual microprocessor receiving this information have to be capable of doing two operations per clock cycle as well then?
Yep. Yep. But a processor is much faster, right? Like clock signal. So for instance, these could be the signals in a typical synchronous DRAM cell or a chip. So here's our clock, okay? We have a read-write, obviously, control signal. We have to tell the memory unit whether we're reading or writing. And we still have these strobe signals, but we only have to activate them once now for a burst of data. Down here we have the address, row and column, and here's the actual data that's being, let's say, read out from this particular cell. So what happens is that the control circuitry will say, okay, well, we want to read a bunch of data, okay, in a particular row. So it's going to activate this. We're going to read. So it goes active high for this particular clock cycle. At the same time, the row address strobe goes low, meaning the address information on the address bus is for a row. So that's going to be read in by the chip, okay? I don't know, perhaps on the rising edge of the clock, or it could be the falling edge, whatever, okay? On one of the edges of the clock, when this goes low, the chip is going to read in the row address, okay? Now, it's going to take some time for the chip to activate that particular row in the cell array. In this case, it looks like it's going to take 1, 2 additional memory clock cycles for that to happen, okay? So the row address goes here, this goes low, that gets latched in, the memory chip goes and activates that row. 2 cycles later, once that row is activated, again, the read-write is still high. The row access strobe stays high or inactive, and now the column access strobe signal goes low. Okay, meaning that the address information on the address bus now designates the column of the first word of data that we're going to read out of this memory chip. Okay, it takes maybe a clock cycle for that to happen, and then we read out the first byte of data. Okay, now the control circuitry can tell the chip that, well, we actually want to read out not just the first one, but the first 4. Okay, we no longer need to activate the column access strobe, but the chip can use just every clock cycle, it'll just read the next byte until the specified number of bytes or words have been read out. okay? So now instead of waiting, 2 plus 1, well, I guess it would actually take 1, 2, 3, 4, 5. It would take 5 clock cycles to read out the first one. Instead of waiting another 5 clock cycles to read out the second one, it just happens on the next clock cycle. Okay, so that's what the clock does for us too. Yeah.
What is it showing here on the read-write and the two strobes? It appears like there's periods where they're changing.
Yeah, and that just means that it's not valid during that time.
So why is it not held in one?
It would be. I'm not sure why they do that. It would just, for instance, the RAS, it would only be low during this cycle here. Yeah, I don't know why they show this. Yeah, it's a little
That just
misleading.
confuses the issue to me.
Yeah, it's a little misleading. Yep.
So D0 to D3, those would all be in the same column?
They'd be all in the same row.
And the same row, right?
Yeah.
Okay.
And in fast page mode, if you were talking about an asynchronous DRAM without a clock signal, in fast page mode, well, you only specify the row once, but you have to specify the column every time, right? Which takes 2 clock cycles. So that means you'd have 2 clock cycles between each of these if there was a clock in an asynchronous, which there isn't. But with the synchronous, it can be even faster. Just every clock cycle, out comes another byte. Okay, because it's the clock cycle that is driving that. You only have to specify the row once. You only have to specify the column address for the first byte, and then the control circuitry will just update it for each one after that on every clock cycle.
So that's like a characteristic of the burst mode, is it just automatically
Yep,
increments?
yep. This is what we would call burst mode. And synchronous DRAM chips typically have this, yep.
So does that mean that the row, like the RAS and the CAS, they're always going to be inverted because you can only look at the column or the row?
Yeah, because typically we multiplex the address pins anyways. So at any particular time, the address pins will either have the row address on them or the column address on them. So you don't want to activate those both at the same time.
Like in an exam, if we have to draw this, once you've done one, you can almost invert your other one. Because it's like,
Yeah.
it'll be happening, it's one or the other
Yeah.
operation.
Yep. Yeah, because typically we're trying to reduce the number of external pins on the chip, which means that we use the fewest address lines possible, which means you share them between the row and the column. Obviously not at the same time, yep.
Is the number of bytes read determined by the RAS, when the RAS goes up, or?
No,
like
no,
what
the number of
determines
bytes,
The number of bytes.
the number of bytes would be, that's what happens. I think they're just not telling us. It specifies how many bytes are read out, right? And I don't think this one,
Yeah, so first thing we have is the row RAS. It goes down, and we know that that is a row address.
yep,
Now, the column address, or the cast or whatever, is also at a high.
Yep.
How does the cast know that that's not information that it's supposed to interpret as a column? How does it know that it has to wait until the next one?
well, because it,
So, wait, on that diagram then, is it not active low, like when the RAS goes low,
Yep.
the cast goes high, and then right after that, it goes low? So
yeah, this is, as Murray said not long ago, this picture is very misleading. Assume that the signal looks like this. And this one is going to look like this. Yeah, I don't know why they put that in there. It's,
So then, Max's question was that you would just draw the inverse, so now we can no longer just draw the inverse.
well, no, I believe what he was saying is that if this goes low, this one must be high. And if this one's high, this one must be low. Because you can only latch in that address to the row or the column circuitry.
Right,
These can't be low at the same time.
right,
I believe that was his point.
okay.
Yeah, because it's the same pins that are holding the row and column address. Right, so the control circuitry is going to put the row address on there first, drop this low, that row address gets latched into the row decoding circuit, right? Then sometime later, it's gonna put the column address on those same address pins. This goes low, indicating, okay, it's a column address, latch that into the column decoder. Okay, and then the circuitry, and a good question posed was, well, how do we know how many bytes? That many bytes get loaded out or read out on every clock cycle. Okay, so there's more here below the surface that they're not telling us, but we're sort of hitting the high points. Okay, instead of reading out data, say for over one clock cycle, maybe on the rising edge of this clock, that's when we read out the data. Well, why don't we read out data on the falling edge as well? Okay. We use the edge of the clock to do something, read out, well, we got two edges. We got a rising edge and we got a falling edge. So why don't we read out D0 on the rising edge of a clock, read out D1 on the falling edge, that way we read out data twice as fast, okay? So that brings up a couple of definitions of, again, trying to quantify the performance of a memory cell. So if we go back to this example, this is when things started, okay, when the row address was put down here and it was strobed in. Well, it took 1, 2, 3, 4, 5 memory cycles before we get the first word out. We call that the latency, okay? How long it takes to read out the first word of a block is memory latency, whereas how quickly can we get out the data after that, we call memory bandwidth in terms of bits per second or bytes per second. Those are two different things, right? You could have two different memory chips. One could have a longer latency than the other, but they could both have the same, once that happens, they both have the same bit memory bandwidth, the same bits per second after that. To get this first word out for a double rate SDRAM could be the same. But after that, the data comes out twice as fast, right? Because it's coming out on the rising and falling edges of the clock. If we go back.
You said that you can only do like one operation per clock cycle. So in that case, like how come they can do two things in one cycle with that? Like, yeah, I understand it's like one's on the leading and one's on the dropping. Like, are you using like two, like in the diagram before you have like the app?
Right, if you want to speed up the memory, well, okay, just make the frequency of this higher, right? But of course, there's a limit on that. The memory chip, or the circuitry in the memory chip can't go as fast as you might make this clock cycle, whereas the processor probably can. That's synchronous DRAM. So then somebody said, well, that's what we call double data rate SDRAM. We basically transfer data on both the rising and falling edges of the clock, okay? Because of this burst mode in a synchronous DRAM, we can talk about memory latency and memory bandwidth, where memory latency is the time required to transfer the first word of a block. Okay, so that's two terms that are used for quantifying the performance, memory latency, how long to get the first word out. Memory bandwidth is basically how fast does the data come out after that. So a double data rate SDRAM, because it's transferring data on both the rising and falling edges of the clock, it doesn't really change the latency, okay? The time, so the latency might be the same, but the memory bandwidth is improved. Okay, well, to accommodate two transfers per cycle, often the cell array is going to be organized or separated into two separate banks, okay? Because it's kind of like, what's a good analogy? You know, you've got people trying to get out a doorway like that, right? And it's only wide enough for one person at a time. Well, if you put two doorways in, you get two people out at a time, okay? So it's not a great analogy, but maybe it'll help. To accommodate this two transfers per clock cycle in a double rate chip, the cell it's broken up into two banks, and these words, right? Consecutive words of a given block are stored in different banks. We call that interleaving. Yeah?
With the two transfers per cycle, does that mean that the processor can run at a different clock cycle than the memory?
Yeah, I think
and it
so.
would just double down? Like the
Yeah, I think
frequency
so.
would be twice as high as the processor?
Okay, so we've been focusing on single chips up till now. Obviously, you know, if you open up any computer, you're gonna have multiple memory chips. At least we used to. The chips are probably getting pretty dense these days, but for larger memories, we would have to have multiple chips, okay? So they could be set up something like this, where each one of these black boxes is a physical IC, right? A chip. And so we can now set them up in arrays of chips. So in this case, we've got 4 by 4, we've got 16 chips that make up this large SRAM. So a typical 2 mega word by 32-bit static memory system, where each one of these chips is a 512K by 8 memory chip, meaning that there's 8 outputs, so 8 bits for your output or input, okay, 8 data lines, and there's 512K of those bytes in this chip. Okay, to get 512 addresses, we need 19 bits on the address, right? Because 2 to the 19 would give us 512K. So there's 512K words in here, where a word is 8 bits. So if we want a 32-bit word to be read out at a particular time, we would put 4 of these in a row like this, right? Where this chip will give us the 8 most significant bits of a 32-bit word. This one will give us the next 8 most significant bits, so on, and then the least 8 significant bits would come out of this 4th chip in that particular row. Okay, so one row gives us a 32-bit word, where those 8 bits of those words are of that word is here, 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 and here. Okay, each one of these has 512K rows, if we want to think of it as a row. So 512, 512, 512, we've got 2 meg of rows spread across these 4 chips, right? Each one of these has 512K. 4 of those gives us 2 meg. Okay, so that's what's giving us the 2 meg of words. So we've got, if you look at this all as one array, we've got 2 meg words, where one word is 32 bits. 8 bits here, 8 bits here, 8 bits here, 8 bits there. Okay? So in order to address this, well, we need a row address, and a row address is just going to choose one row of chips. And we've got 4 rows of chips. So therefore, we only need 2 bits to decode which row we want to access. Where a row is a row of chips. Okay? So we're going to only be accessing one row at a time. So these 2 bits go here to a decoder, which is going to activate one of these. We'll call it a word line. Okay? And then we want to access a particular, excuse me. Then we're going to want to access a particular word of 32 bits, okay? So let's say A19 and A20 are 0, 0, which corresponds to this row here. Now we have to choose, remember, each one of these chips has 512K rows in it, as does this, as does this, as does this. So now we have to choose which one of the 512K rows in this chip we want to access, okay? That requires a 19-bit address. So A0 to A18, this address is going to be fed to each one of these chips in this row. So that 19-bit address will access one of the 512K rows in here, the same row in here, the same row in here, and the same row in here. So now we've activated one particular row of chips, and we have activated one particular row in each one of the chips in that row. And then the 8 bits of each of those chips is going to be dumped out or read in the data lines. Okay? Any questions about that? And of course, we can add more rows of chips, add more columns of chips. If we need a 64-bit word, well, then we'd have to add 4 more columns of chips to this. And obviously, the number of address lines is going to increase then. Okay, so we can put multiple chips together, and the address gets divided up like this, choosing rows of chips and then choosing rows within a chip. All right.
The way that it's set up, would it, like, let's say that you were to activate one of the rows on one of those chips, would it activate the row on every single chip in that column?
No, in the row.
In that specific row? Like,
Yep, because these two bits are going to activate one of these rows of chips,
oh, I see.
only one at a time. So if this one gets activated, then these lines, which go there as well, is going to choose one of the rows in each of those chips, but only in this row of chips. Yeah. Okay, so DRAM, go back, SRAM, DRAM, it's going to be organized similar to the slide we just saw. This might be a little bit obsolete now. I'm not sure we still have these, but for the longest time we did, where when you wanted to add more memory to your big desktop computer, what did you do? You popped off the case, you find the motherboard, right? And on the motherboard you would find headers. Headers are connectors. These are the headers down here, right? And you'd see a number of those, and when you bought this thing from the store, there'd be one of these cards in there, because they always sell you the minimum amount of memory unless you ask for more. So when you needed more, you went to the electronics store, you bought one of these SIM cards or DIM cards, depending on whether it was a 32-bit machine or a 64-bit machine, and you just plug another card in there with a bunch of memory chips on it, and voila, you doubled your memory or quadrupled your memory, okay? Yeah, so that's about it. So that's all we need to know about RAM for this course. Okay, well, let's briefly talk about ROM. ROM stands for read-only memories. Okay, obviously RAM, you can write to it and read from it. ROM, we only typically read from it. Okay, they're non-volatile memories. That means that you turn the power off, they retain their value. Okay, and that's because of the way they're fabricated. They're very similar to a DRAM cell, except instead of having a capacitor here, we have an actual switch, if you want to call it that, where the switch gets flipped on or off, and once it's done that, it's permanent. So it's basically a little fuse, which you can either burn out to break this connection, or you can leave intact to keep this connection at ground, right? So if it's connected, obviously we've got ground on this side of the transistor. When you activate that transistor, what do you see on this side of the transistor? You see ground if this is intact, indicating a 0, right? If this is burnt out and this is open, well, now when you activate the transistor, obviously this ground is not going to be here, so this bit line is going to interpret that to be a 1, okay? So ROMs are typically common in embedded systems in place of hard drives, where the software doesn't need to change, obviously, right? So a typical ROM will look like that. Programmable ROM means that you, as the programmer, can actually burn your code into there. All ROM is basically programmable. Somebody has to program it at some point in time. But developers, if you're a software developer, and when I was in industry, I might have told you the story, we were developing equipment that we put into cell site towers in order to automatically locate cell phones, right? This was before every cell phone had a GPS in it. And so our equipment consisted of a box about the size of a shoebox with circuitry in it that we would connect inside the cell towers, and we'd take signals off the antennas and we'd do our magic with that, right? Well, it was driven by software. And so, we were constantly redeveloping the software. We actually, one of my colleagues, he had a master's in electrical engineering. His job was 24 hours a day basically writing assembly code, right? I think somebody asked, well, why do we write assembly code? Well, there's a few people that still do it. In that case, we had a limited amount of memory that we could put into our equipment, and therefore it had to run extremely efficient, and the only way to write the code was in assembly in order to do it. And he would agonize. He'd go home at night and figure out, okay, how can I turn these 3 instructions into 2 instructions? Like, that was his job, because we only had so much memory. But the point here is that he would then assemble his code, and the machine code we would then burn into a ROM chip. And so I'd go out to the cell site, I'd bring the box back because he had a new version of his software, and we'd pop out the ROM chip. He'd have a new ROM chip, pop it back in, run it back out to the cell site and test it again. And so you have to be able to program these. Okay, so the way we did it was, you could reverse, no, not in this one. This one is permanent, right? So you burn out this fuse and it's gone. But there's other types where this is not permanent, okay? And we would call them EPROMs because they're erasable, programmable, read-only memory, okay? So they use special semiconductor techniques. This is basically a transistor, and they use basic semiconductor techniques or complex semiconductor methods to either turn this transistor on or off, indicating there's a 0 or a 1 in this cell, okay? And it would retain that. How did we erase it? Well, the EPROM chip would have a little window at the top over all of these cells, and we put it in a little box that would blast it with ultraviolet radiation, and that would set this transistor back to a state where it's no longer programmed, or it could be programmed again. And so whenever I brought the equipment back from the cell site, we take the chip out, we put it into the UV eraser, and it would have to be in there for 30 minutes, and then it was basically clean again, and it could then be electrically programmed again with the new code. Okay, so that's what we call EPROM, and we'll talk about cache on Monday. Have a great weekend. Stop there, we're basically done.